Good morning, friends. I am Dr. Yagya Dutta Dwivedhi, Professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of taking the lectures on flight mechanics, specifically these lectures on aircraft performance, where we discuss about different phases of the flight, like cruise flight, climb flight, landing, takeoff, and so on. As of now, I am in process of understanding the cruise flight. As of now, we have already done the study on the atmosphere, their layers, temperature, pressure, and density variation of the atmosphere. We have also discussed about thrust required, drag polar, power required, power available, thrust required, different velocities like maximum velocity, minimum velocity, maximum range, endurance, range conditions like constant altitude, constant velocity, constant angle of attack, range. These are things we have already covered. Today my topic is related to the problem and the solution of maximum L by D and the maximum speed. This we will be solving some problems related to this. Before that, we will go for some basic concept on that. So we will see that today's lecture I will be covering the maximum lift to drag ratio, specific speed in straight and level flight, maximum speed, then problem and the solution. I will be taking the two problems related to the different speeds and different conditions. So we will be seeing here maximum lift to drag ratio. So what is the maximum lift to drag ratio? And we have seen that in the previously that if we plot the alpha versus CL by CD for the symmetric airfoil, and this is the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So nearly between 3 to 4, this will go highest and then it will go like this. So this is the point where you have the CL by CD. This is the maximum, and this is the angle between 3 to 4. This is the alpha, that is called angle of attack, in which if you fly, your performance of the aircraft will be high. As a designer, we are the engineer here and we are to design the aircraft. So we should make sure that the CL by CD should be maximum. It is a very important aerodynamic characteristics which directly says that your aircraft efficiency and the aerodynamic performance of the aircraft. So whatever you want to do, any research and other things, make sure that your designed aircraft should be CL by CD should be maximum, and we should also find out that at which angle of attack we fly. If we fly in this angle of attack, our range will be highest, our endurance will be highest, your landing, takeoff, all the performance will be highest. So one of the important parameters in a cruising flight is the lift to drag ratio, that is CL by CD ratio. One of the objectives in aerodynamic design of an aircraft is to design an aircraft that produces the maximum lift with a minimum drag. So CL by CD max. So CL should be maximum and CD should be as less as possible. So we will see that what is the relation between CL by CD and CL to CD, and in which condition we are going to get the best output. So now next, if you see here, lift to drag ratio plays a significant role in the aircraft design process. For a steady level flight, the lift to drag ratio is simply the reciprocal of the thrust to weight ratio. So what it is saying that lift to drag is equal to reciprocal of 1 by T by W. So that is the relation. For a steady level flight, the lift to drag ratio is simply the reciprocal of the thrust to weight ratio. Thus, L by D is equal to W by T, or T is equal to W into D by L, or W by L by D. So, thrust is equal to W by L by D. So, here, if you see for the minimum value of D by L is the reciprocal of the maximum value of L by D. So, this L by D should be maximum so that T will be minimum. Here this T is a thrust required which is directly proportional to the drag. So, here for the thrust minimum, that is minimum thrust required is equal to W by L by D should be maximum. So, if this number is highest, your T will be minimum. So, this T minimum is also called the thrust required for minimum or minimum thrust required. You can write here minimum thrust required. So, T minimum is equal to W by L by D maximum. So, this relationship states that if a pilot intends to have a minimum fuel consumption, that is the minimum thrust, he or she must fly with a configuration that has a maximum lift to drag ratio. So, L by D should be maximum. Pilot has to fly in such a way that L by D maximum. I gave just now the example. This is the L by D or CL by CD, and this is the alpha. So, this is the angle of attack. This is the alpha optimum, and this is the CL by CD maximum. So, pilot has to fly in this L by D ratio, and mostly it is 3 to 4 degree angle of attack. If pilot is flying, the maximum lift to drag ratio we are getting, and if you are getting the maximum L by D, the thrust required will be the minimum. So, fuel consumption will be minimum. So, your endurance and the range of the aircraft will be very high. Aircraft will go very high range. Range is a distance which aircraft covers with a given amount of full tank of fuel. And the endurance is the time which the maximum time the aircraft be in the airborne with a given amount of full tank of fuel. So, to have this more endurance or the more range, the aircraft should fly in such a way that where it is CL by CD is maximum, and this CL by CD will be maximum where alpha. So, this pilot has to fly in this alpha, that where the CL by CD is maximum. So, in a cruise flight, the lift is equal to the aircraft weight. So, in the cruise flight, L is equal to W. So, to maximize the lift to drag ratio, the drag should be minimum. So, L is equal to W. So, to maximize the lift to drag ratio and this L by D to have the maximum, L should be high, D should be minimum. So, L by D should be maximum. So, D should be minimum. That is the criteria, that drag of the aircraft should be minimum. So, we know that L is equal to half rho V square SCL and D is equal to half rho V square SCD. If we divide this equation to this equation, so L by D half rho V square SCL divided by half rho V square SCD, this thing is cancel out. We have here CL by CD. By inspection, we can see that the L by D maximum is equal to CL by CD maximum. Therefore, to maximize the lift to drag ratio, one should maximize the ratio of lift coefficient to the drag coefficient. So, therefore, to maximize the lift to drag ratio, one should maximize the ratio of lift coefficient to the drag coefficient. Drag polar was defined as, we know that drag polar, that is a total drag. CD is what? It is a total drag. This total drag CD is equal to CD naught plus KCL square, where CD naught is the zero lift drag and KCL square is the induced drag. This can be plugged into the ratio of the lift coefficient to the drag coefficient in the previous equation. So for CL by CD, CL, and for the CD we can write the CD naught by KCL square. So in this CD from 2.19 equation we have put this value here in this. So to find the maximum CL by CD, one must differentiate equation 2.20 with respect to the lift coefficient and set the result to the 0. To find the maximum, we have to differentiate this equation with dCl by CD with respect to the CL. So we can differentiate it and we can find that this numerator CD naught plus KCL square minus 2KCL into CL divided by CD naught plus KCL square. So here 2KCL square and here is KCL square. So we will get here CD naught plus KCL square minus 2KCL square is equal to 0. And so here we will get CD naught plus KCL square is equal to 0, or CD naught is equal to, it is minus. So CD naught is equal to KCL square, or CL square is equal to CD naught by K, or CL is equal to under root CD naught by K. So we got this relation that for the maximum L by D ratio, the coefficient of lift should be under root CD naught by K. So here CD naught is equal to KCL square, and if we put this value here in the equation, this one, equation 2.20, so we will get for CD, CL by CD maximum is equal to 2 CD naught. So this relation we have got. The coefficient of drag, that is CD for CL by CD maximum should be 2 times the zero lift drag. This is the ideal condition and which we have to maintain for a best performance. Now this equation that CD is equal to 2 CD naught, 2 CD naught, this we have to obtain. To obtain this implies that when the lift to drag ratio is at its maximum value, the drag coefficient will be twice the zero lift drag. So this drag coefficient CD should be 2 times the zero lift drag. That is the one conclusion. Second one, in other words, the zero lift drag coefficient will be equal to the induced drag coefficient. Another we are getting that CD naught is equal to KCL square. We have got this relation also. So for the lift to drag ratio is highest, CD naught should be KCL square. The zero lift drag should be equal to the induced drag. This is the induced drag, and this is the zero lift drag. So here CD naught is equal to CDI. CDI is a induced drag and CD naught is a zero lift drag. every aircraft has a unique maximum lift to drag ratio. Every aircraft in their flight manual, it is mentioned that what is the maximum lift to drag ratio of this aircraft. By experimentation, they will find out and they will mention in the necessary books. Here if you see I have one table here. This table demonstrate the maximum lift to drag ratio for several airplane category. So if you see the sailplane or the glider, it is very high, 30 to 40 L by D ratio. For jet transport aircraft like Boeing, Airbus, they have the 15 to 20. Light general aviation aircraft like Cessna and all, they have the 10 to 15. Subsonic fighter, they have 7 to 10. Supersonic fighter, they have the 4 to 7. Helicopters, they have 3 to 5. Remote control RC plane, they have 7 to 16. Home built RC plane, you have 6 to 40. So these are the few examples of different types of aircraft which will have different L by D maximum. For sailplane, it is very high, and for fighter plane, it is supersonic fighter plane, and the helicopters are very less. Now, further we will see the derivation of this. To calculate this parameter, equation 2.23 is inserted into the equation 2.20. So here we can write CL by CD maximum, CL by KCL square plus CD naught is equal to KCL square. So here we will get CL by KCL square, 2 KCL square. So this CL and this has gone 1 by 2 KCL. So CL by CD maximum is equal to 1 by 2 KCL, where CL by CD is a maximum. So this we got one more relation here. So when the lift to drag ratio is at its maximum value from equation 2.23, we obtain that CL by CD maximum is equal to under root CD naught by K. This is also very important relation. So CL for CL by CD maximum is equal to under root CD naught by K. When this lift coefficient is plugged into the equation number 21, the following equation is obtained. That is, here CL by CD is equal to 1 by 2, here 2, and here we can write here K CD naught. CL by CD is equal to 1 by 2 under root K CD naught. So here, now we will discuss. So here in this, we will get one more relation, that CL by CD maximum will be 1 by 2 under root K CD naught. This is the condition for CL by CD maximum. Now we will discuss about some specific speeds in straight and straight line level flight. The minimum speed is usually little more than the stall speed, about 1.1 Vs, where Vs is a stall speed. So your aircraft should not go less than 1.1 Vs to 1.3 Vs. So this is the minimum speed, and cruising flight with a velocity less than the stall speed is impossible. You cannot fly the aircraft less than the stall speed. It is impossible. It is very dangerous, and aircraft will start sinking down, and there is a risk of accident of the aircraft. The reason is that the lift force would be less than the weight. The maximum speed in which flight is when the pilot uses the maximum engine throttle. So what is the maximum speed? When pilot is putting 100% throttle, full power available, when aircraft pilot is putting whatever maximum speed you are getting, that speed is a maximum engine speed. Maximum speed is often about 2 to 3 times of the stall speed. So if it is stall speed is 100, so your maximum speed may be 300 for general aviation aircraft, and 4 to 5 times for the jet aircraft, and 5 to 15 times for the fighter aircraft. Specific speeds are of significant importance for pilots and are used at specific flight conditions. Here I will give some examples of specific speeds. First one is the maximum speed. It is denoted by the V maximum. Another is the minimum drag speed, V minimum drag. Speed for maximum lift to drag ratio, that is V L by D maximum. Maximum range speed, V maximum R, max R. Maximum endurance speed, V maximum E. Speed for absolute ceiling. Cruise speed, VC. Every speed has one or more specific application, and a pilot adopts one of them based on the desired mission. Jet transport aircraft is supposed to carry a payload with a minimum cost, while a fighter jet has the mission to fight with enemy fighter. So for the different aircrafts, we have the different mission. If you are the passenger aircraft, our objective is to save the fuel, save the cost of the operation. But for the fighter jet, we are concerned with how much it is destroying the enemy, how much range, with how much speed and the load factor your aircraft is maneuvering. For dogfight, for combating fighter aircrafts, these are the roles. So accordingly, different aircrafts will have different types of speed. A surveillance aircraft has to fly over border to protect it from illegal trespassing. So if it is surveillance aircraft, we need more L by D so that the endurance of the aircraft should be high. So now we will discuss some speeds, that is the maximum speed, that is Vmax. One of the most important performance criteria for any aircraft is maximum speed. It is V maximum. This is achieved when the maximum engine thrust is applied. So just I will give here one. This is the velocity and this is the here thrust. So if this is the your power required or thrust required, and this is the thrust available. So this is the point. This is the Vmax. In this, your pilot will give the full throttle. Your whatever power is available, in that your aircraft will fly, and this is called the maximum speed, and this is achieved by using the maximum engine thrust, and it is by the maximum throttle. 100% throttle is to be applied. It is highly recommended not to use with the maximum thrust in a long flight to reduce life and the fuel cost. Only in case of emergency, we should go for the highest speed. If you go for highest speed, the life of the engine will be reduced, lot of stresses will be developed in the aircraft body, and the fuel cost, because it will consume very high fuel, so the fuel cost will be increased. Only in case of emergency, you should go for the maximum speed. When comparing two aircraft, one with a higher maximum speed is pronounced to have a better cruise performance. So if there are two aircraft A and B, this is the A and this is the B. If A has got 500 knots, this has got 400 knots B. So A is assumed to be better cruise performance. The aircraft which is having more higher speed, that aircraft can perform better. It can do lot of maneuvering, lot of things it can do because it has more power. Engine power has got more. Experimental aircraft X-15A, highest maximum speed of 7,297 kilometers per hour of Mach number 6.72 on October 1967. So X-15 aircraft were developed as experimental, how much it can achieve maximum. So it has achieve the 6.72 Mach, and that is to 7297 kilometers per hour. Now we will discuss about effect of altitude on the aircraft. Increase in altitude has several impacts like reduction in lift, drag and the thrust. To compensate for the lift reduction, the CL or the alpha to be increased. The increase in CL will increase drag coefficient also. So, as you go high altitude, the density is reduced. This reduction in the density will reduce the lift. To compensate this lift, we have to increase the CL or angle of attack. If we increase the CL, your drag coefficient will also increase. So as you are in higher altitude, you will experience more drag. At low altitude, maximum speed is increased, but at high altitude causes a reduction in the maximum velocity. So at low altitude, you can achieve the maximum speed is increased, but at high altitude causes a reduction in the maximum speed. So if you are flying at a 1 kilometer, your speed is 500, but if you same aircraft, same condition, if you 5 kilometer to 10 kilometer, your maximum speed will be 400. It will be reduced because your engine thrust will be also reduced. There is usually a specific altitude that the maximum speed reaches its absolute maximum, that is V maximum. Okay, so there is usually a specific altitude, a certain altitude that the maximum speed reaches its absolute maximum. This altitude is one of the favorite altitude to fly when the pilot is going to absolutely maximize its maximum speed. Therefore, the maximum air speed is a non-linear function of the altitude. So, as you go altitude higher and higher, your speed will be differing. So, it is a function of the non-linear function of the altitude. Let us see how to analyze and calculate this absolute maximum speed and its corresponding altitude in a cruise flight. So, let's lift is equal to drag, and this is the equation of motion for cruise flight. For maximum also this can be applied. So this we can see for thrust maximum, the drag maximum half rho V square maximum S into CD, and we already determined the drag polar and the lift coefficient as CD is equal to CD naught plus. So if for the thrust maximum, drag will be maximum and the velocity will be maximum. We know that total drag, it is determined from the drag polar, and here the CD is equal to CD naught plus KCL square, where the CD naught is zero lift drag or parasite drag, and KCL square is induced drag component. So we have two types of drag. One is the induced drag, another is the zero lift drag and the parasite drag. So here we can see that here lift is equal to weight and half rho V square S CL. So we can write that CL is equal to 2W divided by rho V square S. So this is mentioned here. For the maximum condition, your velocity will be maximum. So here we have mentioned the maximum velocity. By substituting equation 2.10 and 2.12 into equation 2.29, and we have seen that if you put here, so this is the half rho V square S CD. In place of CD, we can write here CD is equal to CD naught plus KCL square. So in this half rho V square CD naught plus here half rho V square KCL, we can put 2W by rho V square S. So here you will get here that T maximum is equal to half rho V square maximum S CD naught, and here half rho V square S into 2W by rho V square S. Okay, so and so we will get here that CL is square. So this is the square. So what we will get? This rho V square and the rho V square here we will get 2K. Here K is there. So 2K W square divided by rho V square S. So this we are putting here. So you will get this value. So total thrust maximum is equal to half rho V square maximum S CD naught plus 2K W square rho V square maximum S. This is the equation. To have this maximum, to have this thing maximum, we can make it that half rho V square S CD naught plus 2K W square rho S 1 by V square minus T max is equal to 0. Now we will see that we can put this thing A, this is the A, this is the B, and this is the C. So you will get here A V square plus B by V square maximum minus C T maximum is equal to 0. So where A is equal to half rho V square CD naught, B is equal to 2K W square by rho S. Here C is equal to rho by rho naught to the power 0.9 for the turbojet in troposphere. C is equal to P 11,000 by P naught to the power 0.9, rho by rho 11,000 for the stratosphere. C is equal to rho by rho naught 1.2 for the turbofan engine. These are the some criteria for different types of aircraft where C is a ratio of the density. For the different condition, it is mentioned in this here. So in this equation, only unknown is the V maximum and has order of 4, which gives 4 solution, and the highest solution is accepted. So we will get 4 values. In that, the highest value of V is taken in this equation, where rho is air density at any altitude, rho naught is air density at the sea level, P 11,000 is air density at 11,000 meter of altitude. Okay, now we will see the one plot for variation of maximum speed. Here the altitude versus velocity is given here. So here is the Vt, it is for the thrust, and it is for the green is for the turbo, and this is for the propeller engine. So it is falling like this. As you go high speed, at high altitude your velocity will be less. As you go high speed, your altitude at sea level you can fly high. But if you see the turbojet, it is like this. There is not much variation. So there are two types of engines and both have the different parameters. Equivalent airspeed always decreases with altitude. This is the equivalent. VE is equivalent speed and VT is true airspeed. So the true airspeed is increases at the beginning but decreasing afterward. So equivalent airspeed, that is VE, always decreases with altitude, but the true airspeed increases at the beginning and decreases afterward. So beginning it is increasing and after that it is decreasing. explanation of maximum speed. So what is the maximum of maximum speed? So we will see there the maximum true air speed has an absolute maximum, that is the maximum of the maximum air speed. Based on this graph, every aircraft has a maximum speed at each altitude. However, the maximum of maximum speed occurs only at one altitude. This altitude depends upon such parameters as aircraft weight, engine power, and the thrust, aircraft zero lift drag coefficient, and the configuration. So maximum of the maximum lift is depend upon the following parameters. So this we have to see it. Now we will see some two problems, numerical problems, and we will apply these equations which we have learned just now. So first problem is the aircraft Cessna Citation 2 has the following features. CD0, that is zero lift drag, is equal to 0.022. Oswald efficiency E is equal to 0.85. Aspect ratio 8.3. Mass of the aircraft is 6032 kg. Area of the wing is 30 meters square. A, that is the slope, lift slope, CL alpha is 5.91 per radian. Stall speed is 82 knots. Thrust maximum is 22,240 Newton. We have to determine ABCD, that is the maximum lift to drag ratio. What is the angle of attack corresponding to the maximum lift to drag ratio at sea level, assuming alpha naught is equal to 0, means it is symmetric airfoil. What is the air speed corresponding to the maximum lift to drag ratio at sea level? What is the minimum required thrust for this aircraft to use? So first we have to find out L by D maximum, then angle of attack alpha, then we have to find out the airspeed for maximum L by D, and minimum required thrust TR minimum. These are the things we have to find out, and we will see that how we are going to handle this problem. So if you see here, given parameters, we know that CD naught is equal to 0.022, E is equal to 0.85, aspect ratio is equal to 8.3, mass M is equal to 6032 kg, area S is equal to 30 meter square, A is equal to 5.91 per radian, stall velocity is equal to 82 knots, T maximum is equal to 22240 Newton. These are the given characteristics. So we will see the first one, A, that is CL by CD maximum. How to find out? So we know that CL by CD, just now we have derived the CL by CD maximum is equal to under root 1 by 2 under root K CD naught. So here CD naught is given, we have to find out the K. So we know that K is equal to 1 by pi into E into aspect ratio. So here 1 by 2 into 1 by pi 3.14 into 0.85 into aspect ratio 8.3. So K we will get 0.045. If we put this value CL by CD maximum is equal to 1 by 2 under root K 0.045, and from here CD naught is given 0.022. So if we solve this, we will get 15.89 or 15.9. This is the CL by CD maximum. This is the answer for this problem. So if we see the problem B now, in problem B it is asked that find the angle of attack. What is the angle of attack? This is the problem. So we know that A is equal to dCl by d alpha, and this is given. It is given 5.9. A is equal to 5.91. It is given. A is given, and this is dCl by d alpha. So we have to find out this alpha, and we should also know the CL. So what is the CL? CL is equal to maximum CL CD naught by K. We know the CD naught is 0.022 divided by K. We have got 0.045. So you will get 0.69. So we got the CL. We have, so we will put here. So 0.69 by alpha is equal to 5.91. So alpha is equal to 0.69 by 5.91. So you will get this alpha is equal to 0.11 radian or 6.7 degree. So this is the angle of attack answer. So this is the problem number. This is the part B. Now we have to find out the part C. So here we will see the part C. In the part C, we have to find out the velocity. Velocity V. So we know that for the cruise condition, lift is equal to weight, and this is half rho V square S CL. So V is equal to 2W divided by rho S CL. So under root 2 into mass is here 6032. This is the mass. 6032 into 9.81 to kg to Newton. Rho is 1.225. S area is here 30 meter square. Into CL we have find out 0.69. So you will get this velocity 132 point. You will get this velocity in meter per second, that is 68.3 meter per second, and this we can convert to 132.82 knots because speed of aircraft is represented in knots. So this is another answer. So we have got the three answers. One answer is this, another is this, and another is this. Now last problem in this, we have to find out the thrust minimum. This is our next issue. So how to handle this? So we know that the condition for this CD is equal to 2 CD naught. So 2 into CD we have 0.022. So this is 0.044. For the minimum thrust, total CD should be 2 times of the CD naught. And we know that this thrust minimum is equal to half rho V square S CD. So half into 1.225 V square we have find out here, so 68.3 square into area is 30 into CD is equal to 0.044. So we will get thrust minimum is equal to 3771.5 Newton. So this is the answer for the final section of this thing. So we have find out the K on the maximum CL by CD. Then we have find out the angle of attack. Then we have find out the velocity for this maximum CL by CD. And also we have find out the thrust required minimum for this condition. Now we will go for the next problem. That is your second problem. Problem number 2. A large jet transport aircraft with a mass of 165,000 kg, an engine thrust of 320 kilonewton, and a wing area of 260 meter square has a zero lift coefficient of 0.02 and the K is given 0.05. Determine the maximum speed at sea level. So we have just now, if you see, we have derived this equation for the maximum speed here. So here we got the maximum speed. So we have to use this equation and we have to find out all these things. So we will see here that what things are given in this problem. If you see here, mass and the thrust is given. So in this given, mass of the aircraft M is equal to 165,000 kg. Then we have another thing, engine thrust is equal to 320 kilonewton, 320 into 10 to the power 3 Newton. Then area and the drag coefficient. Area S and CD naught. Area is 260 meter square. 260 meter square. CD naught is 0.02 and K is equal to 0.05. These things are given here and we have to find out maximum speed at sea level. So V maximum at sea level we have to find out. Okay, so we know that the equation we have just now find out that AV square plus B by V square, that equations we have to use it here. And so we know that A V square plus B by V square maximum, all are maximum, minus C T maximum is equal to 0. This equation we have already derived, where A is equal to half rho S CD naught. So we have to find out half into rho is equal to 0.5, S is equal to, so here 0.5 into 1.225, area is equal to 260 meter square, CD naught is 0.02, so 3.182. This is, we got the A. Now to find out the B 2K W square divided by rho S, 2 into 0.005, W is equal to 165,000 to the square into 9.81 to the square divided by 1.225 into 260. After calculation we get 8,22614.701. This we got the B. Now we have to find out the C is equal to rho by rho naught to the power 0.9. So you will get 1 because it is at the sea level. Sea level, you will get 1. So now we will use this equation that A V square plus B by V square minus C T max is equal to 0. So now A we got here 3 point. A we got 3.185 V square V max square plus B we got 822,614.701 divided by V square maximum minus T we got 320,000 is equal to 0. So here we will get V max by solution of this. V max we will get 4 answers. Out of that the maximum value is here 285.8 meter per second or 556 knots. This is the answer. The Mach number of this is 0.84. It is in the critical Mach number. So this is the solution for this problem. So next topic we will having introduction to ceiling, types of aircraft ceiling, cruising altitude of Boeing 747, variation of flight cost with respect to the altitude, effect of altitude on performance. We have the references from Anderson JD, Aircraft Performance and Design, International Edition, McGraw-Hill's first edition, 1999. SL by ME, Aircraft Performance Theory and Practice, AIA Education Series. Any questions you are welcome to ask in this is my email, ydwivedi@gmail.com. Please do like and subscribe. Give the comments in the comment box. I will try to reply your comments. If you feel any clarification, you are always welcome to ask. Till then, goodbye. Thank you very much for the joining. Be tuned for my next lecture. Till then, goodbye.
Like, share and subscribe. Hit the bell icon for more updates.